My name is AntiQ, and this is joint work with Doug James. We present fast linking numbers for topology verification of loopy structures. Here's a simulation of a chainmail pile. Each sheet consists of interlinked rings. Unfortunately, in this case, a ring falls off and rolls away because a collision is missed between rings. This error is hard to catch visually. If we simulate something, how do we know it's right? The same Chrono simulator was also used to prepare a chainmail dress for 3D printing by packing it into a box. If we want to use a simulation to aid in manufacturing, how do we verify it's right before printing it out? Here's a simulation we computed of a Kusari chainmail shirt. There aren't obvious visual errors here, but is it correct? Our method says no, there are broken links. Let's also look at yarn level cloth modeling. This sweater model was relaxed using a yarn level simulation. Do we know if it's topologically correct? How do we know whether the relaxation avoided pull-throughs and maintained the yarn topology? Watch our detailed talk to see how we found an error in this model. So in this work, we propose fast linking numbers, a topological certificate for loopy structures. Given the model state, our method will compute a linking number certificate before or after processing to enable automatic topology verification. Our other contribution is a systematic evaluation, or bake-off, of methods to compute this linking number certificate. A linking number between two oriented closed curves measures how many times one curve winds around the other. It is invariant under link homotopy, which is any deformation where the curves don't cross each other. In fact, during a single yarn pull-through, the linking number must change. Our certificate is therefore a sparse matrix of pairwise linking numbers. We explore and comparatively evaluate many ways to compute the linking number. One way is by projecting onto a plane and counting crossings, and another way is by computing the Gauss linking integral. Our method uses 3 stages to efficiently compute the linking matrix. Given an input set of loops, we first compute a list of potentially linked pairs of loops. Then we carefully discretize the curves into polylines, and finally we process the polylines to compute a sparse triangular linking matrix. This is the final certificate. 2 structures with the same linking topology would have the same matrix. Here are some results. We packed the Kusari chainmail shirt from earlier into a box to be ready for 3D printing. It is made of rigid curved rings, which we simulate with Bullet and Houdini. The simulation takes 15 minutes to complete. This simulation takes large steps. The left video shows the simulation, and when violations are detected, the corresponding rings are marked in red in the right video. You can clearly see the many violations in both videos. Here's the simulation I showed you earlier, which takes medium steps. Now you can see that a few links are still broken. Now let's try this again with much smaller steps. We verified that the topology is maintained throughout this simulation. Here's a yarn level cloth simulation where we take a sweater and drop it onto the ground. Topology violations are marked in red. Here's a rerun with smaller time steps. Both simulations took many hours to complete, but only a fraction of a second to verify each frame. Now let's drop 1,000 separated rubber bands onto an inclined plane. In the simulation with large steps, violations we detect are highlighted in red. Now we use smaller steps, and our method verifies that it is valid. In this example, we started with a vellum simulation of a glove as a deformed tet mesh. We simply animated our glove yarn model as an embedded deformation, and our method verifies that the topology remains valid. Here's the final render. Can we verify non-closed curves? Yes, a braid consists of 2 rigid bars with curves attached between them, and it turns out we can also verify braids. In this example, we attach a knitted chevron pattern to 2 rigid bars, making it a braid, and verify its relaxation as the bars are slowly pulled apart. Watch our detailed talk to learn more.